Alright, in this video I'm going to talk about one more standard assumption on the preference relation, that is a convexity assumptions. So convexity assumption is concerned about the exchange rate one individual is willing to accept. In other words, marginal rate of substitution, okay, in case of two goods. Alright, so the formal definition of this convexity assumption is we say preference relation is convex so if for any three bundles, okay, x, y, z, such that the consumer prefers y over x and z over x, okay, then any linear combination between y and z dominates the bundle x, okay. So it can be simply interpreted as if consumer prefers y over x and z over x, then any average bundle, so any mixed bundle between y and z will be weakly preferred to bundle x. All right, and then equivalently, we can say, convexity assumption is satisfied for every bundle x. Its upper contour set is a convex set. Okay, so its geometric interpretation is right here. So we choose a one bundle here, x, and think about its upper contour set. Okay. And then we choose two bundles inside the set, meaning that bundle y is better than bundle x, and bundle z is also better than bundle x. Okay? Then it's linear combination. So this line segment joining these two bundles is inside the upper contour set. Okay? So that is another definition of convexity. Right? So its consequence is if the upper contour set is convex, then we can see that indifference curve has a indifference curve has a convex shape toward the origin like this. Okay, so it is instructive to compare these two figures. So this is an example of a non-convex preference. Okay, so now the upper contour set is a non-convex, because we choose these two bundles y and z, then the portion of the line segment joining these two bundles is outside of the upper contour set. Okay, so in that case, indifference curve, the frontier of this upper contour set is not convex, but rather concave in this case. Okay? All right, and then its strong version. So strong version of convexity can be also defined. So strictly convex. So strictly convex can be defined this way. So if we have two bundles y and z, so y is better than x and z is better than x2. Okay, and y and z are not exactly the same bundles. So y is better than x, and z is better than x, okay, and y and z are not equal to each other, okay, and it's linear combination. So the linear combination of y and z, alpha times y, 1 minus alpha times z, okay, so that is strictly better than bundle x. Okay, so then we say preference relation is strictly convex. Okay, so the key is this strict one. All right, so according to convexity assumption, if the consumer mixes up two bundles, he would be better off. Okay, so he doesn't like a extreme bundle, like a one bundle having fairly large amount of good one and small amount of good two. Okay, and this bundle has a large amount of good two, but relatively small amount of good one. Okay, so rather than these two extreme bundles, consumer prefers average bundle. Okay, then preference relation satisfies convexity assumption. All right, and another implication of convexity is, so if we have a convex preference, then upper contour set is going to be convex. Okay, so the indifference curve has a convex shape toward the origin. So consequently, marginal rate of substitution is diminishing over x1, meaning that as consumer consumes more and more good won, okay, then exchange ratio is decreasing. Okay? So that is quite intuitive, right? So if he has a more and more of good won, the marginal utility of the second good gets larger and larger. So consequently, marginal rate of substitution is decreasing. Okay? And it also has an implication on the utility function. So if the preference relation satisfies a convexity, then the utility function representing that preference relation, so function u, is going to be quasi-concave. Okay, so we encounter very important notion in microeconomic theory, quasi-concavity. So its general definition, so its standard definition is right here. So we say function f is a quasi-concave if every upper contour set, so function has a larger value than some constant k. Okay, so this is the set of elements in the domain such that function takes a larger value than k. So it can be thought of as an upper contour set of this function k with respect to constant k. Okay? It becomes a convex set. Okay? So if it is a convex set for every k, then we say function f is quasi-concave. Okay? So its main property is its definition is easy to understand when we draw the function over the unidimensional space. Okay, so here is a graph of the function. F of x is defined over x, and x is a unidimensional space. Then its graph has a single peak like this. Okay, so for every k, if we think about the upper contour set, so where this function takes a larger value than this constant k over this interval, and this is a connected interval, so it is a convex set, right? So if the function has a two peaks like this, okay, then the upper contour set is going to be this connected interval. Okay, so given this k, then the function takes a larger value over these two disjoint and disconnected intervals, and this is non-convex because its linear combination is naturally outside of this set. Okay, so function defined on the real number is quasi-concave if and only if the function has at most a single peak, right? So monotony increasing function or decreasing function is also quasi-concave, right? So think about the increasing function, then its upper contour set for any arbitrary number k is going to be connected interval. So it is a quasi-concave. It is convex set, right? And decreasing function is also quasi-concave. Now the upper contour set is this, and that is connected interval. Okay? Right. So if the function has a peak, it has to be a unique for quasi-concave. All right. So this is a weaker concept that concavity. So I think in unidimensional space, so single variable function, I guess you guys know the exact definition of concavity. So if we have a function f of x that is concave if the second derivative is negative, right? So it has this kind of shape, right? And if we have a multivariable function f of x and y, so the function depends on two variables, then it is concave if the Hessian matrix is negative semi-definite. Okay, so Hessian matrix is defined as for second order derivatives. So f sub xx, f sub xy, and f sub yx and f sub yy. Okay. So here subscript implies the partial derivative. So f sub xx is a second order derivative with respect to x. So we take the partial derivative with respect to x twice. And this cross partial xy, we take the partial with respect to x and with respect to y. Okay? And now we change the order, but does not matter because these two are the same. And the last is a partial derivative, second order partial derivative with respect to y alone. Okay? So if this Hessian matrix is negative semi-indefinite, meaning that this first entry is negative, okay, and determinant of this 2 by 2, so f sub xx, f sub yy minus f sub xy squared is positive. Okay, so if the sign alternates like this, then the multivariate function f is going to be concave. Okay, so here's the definition of concavity, but one weakness of this concavity is it is not an ordinal property, meaning that it is not preserved under monotone transformation. Think about the f of x given by square root of x. That is a concave function, right? But if we take a monotone transformation, say g of x is given by x cubed, right? So now if we compute the composition, g of f of x, that is going to be x to the power, so let me change to x to the power 4th. Okay, then composition becomes x squared. That is not concave anymore, it is convex, right? So although the original function is concave, monotone transformation is not necessarily concave. Okay, so it is a not ordinal property. But quasi-concave, on the other hand, is ordinal property. So if some function is quasi-concave, then any monotone transformation is also quasi-concave. Yeah? All right, so, and one more implication of this quasi-concavity is, if the function is quasi-concave, then we want to solve this optimization problem, x and y, okay, x and y. So if the function is quasi-concave, then it has a the solution to this optimization problem has a nice property. I'm going to explain that in the next video when I explain the utility maximization problem. Okay. All right. So as of now, the only thing you have to remember is if the preference is convex, then upper contour set is going to be convex. So utility function representing this preference relation is going to be quasi-concave. Okay, and quasi-concave is an ordinal property. All right. And if the preference relation is strictly convex, then function u is going to be strictly quasi-concave. Okay, strictly quasi-concave. All right. All right. Right, so in the next example we are asked to find whether given utility function exhibits convex preferences or not. Okay? So here we have u of x. Okay? So there are several ways to verify convexity or not. First, we can compute marginal rate of substitution. So here MRS is going to be marginal iterative from good 1 divided by marginal iterative from good 2. So mu1 is going to be partial derivative of this function with respect to good 1. So we have x2, 1 plus x2. And marginal iterative from good 2 is going to be x1 plus 1. Okay? So that is a decreasing in x1. Okay, so going back to the figure, if the preference relation is convex, then it has a diminishing marginal rate of substitution. So as x1 increases, the slope of the indifference curve is decreasing, right? So here MRS turns out to be decreasing, so we can say given utility function is so the preference relation represented by this utility function is convex. Okay, so another way to verify convexity is we can compute the Hessian matrix. So Hessian matrix H is going to be, now we take the partial twice with respect to 1. Okay, so we take the partial here, 1 plus x2, so that is equal to 0, right? Now we take this function mu1 and then take the derivative, partial derivative with respect to x2, it gives us 1. Okay, and by Young's theorem we know two cross partial derivatives are equal to each other. So f sub 1 2, this is going to be f sub 1 2, or f sub 2 1. This is f sub 1 2. This is f sub 1 1, and we have to figure out f sub 2 2. Okay, so f sub 1 2, f sub 2 1 are equal to each other. You know, the order of taking partial derivative does not matter. Okay, and finally f sub 2 2. Now we take mu2, take the derivative with respect to x2. Okay, and those are constants, so we have 0. Okay, so the associated Hessian matrix with this utility function is going to be this 2 by 2 matrix. All right, so the first entry is 0. Okay, and the determinant is -1. Right, so it is a negative semi-definite. Did I say? Let me go back to definition. Right, so we allow the possibility that that is equal to 0. Okay, so that is a semi-definite. Okay, is a strictly negative, then it's a negative definite. Okay, strictly negative and strictly positive, then this Hessian matrix is negative definite, but semi-definiteness allows for, you know, some principal minor being equal to 0. Okay. All right, and for this one, this is slightly complicated, but we can first make use of the fact that, you know, representation has an ordinal property, right? So any monotone transformation also represents the same preference relation. So we can start with, you know, scaling up. So by taking square of both sides and define this function v, so v of x. Now we can take away, so we can take off this square root. So x1 squared plus x2 squared. Okay, so this function v, monotone transformation, and original function u represent the same preference. Okay, so we can work with this function v. Okay, and its Hessian matrix is going to be 2 0 and 0 2. Okay, so the first entry is a positive and second entry is a positive, right? So second principal minor, so the determinant of this 2 by 2 is also positive. Okay, so it's a positive definite. Okay, so if every principal minor, so these two guys are, so every principal minor remains positive, then we say that Hessian matrix is a positive definite. So its implication is the function is strictly convex. It's a strictly convex. Okay. Before going back to so before doing that, let me go back to the previous example. So, you know, the Hessian matrix turns out to be negative semi-definite. So we can say U is concave, and concavity implies quasi-concavity. So U is quasi-concave. Okay? Meaning that preference relation is convex. Okay? All Right, so for the second example, utility function turns out to be strictly convex, so it is not quasi-concave, right? So it's rather quasi-convex. So it violates, so the preference relation captured by this utility function is not convex. All right, then we have a find standard utility functions, okay? Those are, those satisfy the, previous assumptions. So, preference relation captured by these 5 standard utility functions are rational and continuous and monotone and, convex, okay? So the first type is linear preference, okay? So utility function is given by a linear function like this. So in case of 2 goose, u of x is alpha 1 x1, alpha 2 x2. Okay, and here alpha and alpha 2 are strictly positive. Okay, so in general definition, alpha sub I is strictly positive. Okay, so I think you remember that. So in case of linear preferences, indifference curve is going to be line segment, right? So that corresponds to the case 2 goods are perfect substitutes. Okay, so it can be substitutable at the fixed ratio, right? And the so this is a one extreme case, and the opposite case is a Leontief preference. So it describes perfect complements. Okay. So nav function u is given by minimum of a times x1 and b times x2. Okay, and the indifference curve has a L shape now, like this. Okay, and its slope. So the slope of this dotted line that connects the kink of this L-shaped indifference curves has a slope. So this is A and this is B, so A or B. Okay, so the slope of this dotted line amounts to A over B. Okay, so once again it describes the situation 2 goods are perfect complements. Okay, so standard example is left and right shoes, or PlayStation device, and the game titles. So without the other good, just a one good alone does not generate any utility. Okay, and the third type is Cobb-Douglas preference. Okay, so in case of 2 goods, it has a x1 to the power alpha and x2 to the power beta. Okay, so in case of L goose, we can use this how do I call this? I forgot the exact name, but it's a product of these terms. Okay, so in case of 2 goose, Cobb-Douglas preference exhibits this kind of preference, or this kind of utility function. All right. All right, and then the next type is a CES preference. So CES is a acronym of elasticity of substitution, constant. So constant elasticity of substitution. So we are going to talk about this elasticity of substitution when we talk about pro-auction. So in classic consumer theory, this CES has no meanings, no economic meanings, but it has much more meanings when we talk about pro-auction theory. Okay. Anyway, if the preference relation has a CES, then associated utility function takes this form. Okay. So here the key parameter is R. That is related to the elasticity of substitution. Okay. So elasticity of substitution is defined as the 1 over 1 minus r. Okay, so here parameter r is a number between negative infinity and 1. Okay, so the key feature of this CES utility is if r is equal to 1, okay, then you can easily check utility function becomes linear preference. So utility function becomes linear. So ax1 plus bx2. Okay, so when r is equal to 1, this parameter r is equal to 1, then CS function exhibits linear preferences. Okay? And then the second fact is not straightforward, but it can be shown that as r goes to 0, okay, then x1 r to the power r is going to approach 1, but its exponent 1 over r approaches infinity. Okay, but remarkably, in that case, the function converges the Cobb-Douglas utility. So it converges to x1 to the power a and x2 to the power b. Okay, so it can be shown with a L'Hopital rule. That is some kind of tool we can adopt. The limit of a function is not that well defined. Okay, but I think that is a little bit technical, and then is a kind of not economics, but some mathematics. So let me skip that. So if you are interested, then you may refer to exercise 3.6 C.6 in the textbook. And then finally, as r goes to negative infinity, so the left-hand point, right? And the function converges to Leontief, so minimum of ax1 and bx2. All right, so depending on the value of r, this CS preferences, also CS utility function, incorporates the previous 3 utility functions. So it includes linear preference and Leontief preference and Cobb-Douglas preference. Okay? And one more important fact about this CS utility function is the next, right? Homothetic. Right? So we say preference relation is a homothetic if it satisfies, so if x is indifferent to bundle y, then any scaled bundle alpha times x, so here alpha is a constant, alpha x is also indifferent to alpha y. That means if we compare 1, 2 and 2, 1, right? So suppose that they are indifferent, okay, to some consumer, right? So with that preference relation, then preference relation is homothetic, then 2, 4, 4, 2 also indifferent, and 3, 6 and 6, 3 also indifferent. All right. Consequently, so the marginal rate of substitution, the slope of the indifference curve, has the same value along the ray from the origin. Okay, so here, if we compare x and 2x, okay, and then the marginal rate of substitution at these 2 distinct points have the same value. Okay, and if we draw another ray from the origin, okay, so y and 2y, and these 2 have the same marginal rate of substitution. Okay, right. So if the utility function is a homothetic, preference relation is a homothetic, then the only information we need for figuring out the preference relation is just the one single indifference curve. If we know the value of MRS along this indifference curve, then we can compute the marginal rate of substitution at any other points, right? Because if we know MRS here, then we can figure out the MRS at this point. Okay? So if we know information about MRS for just one single indifference curve, then we can find out the MRS of MRS at the other bundles. Okay, so that is a major property of homothetic preference. Okay, so regarding this, there's one more property that is so if preference relation is homothetic, then its associated utility function is homogeneous of degree 1. Okay, so if this is a homothetic, then U representing this preference relation is homogeneous of degree 1. Okay, so that means U of x1 comma x2, right? So suppose that we scale up x1 and x2. So here, given function U, we have given function U, and then we scale up, both commodities by alpha. Okay, then its value is going to be alpha times U of x1 and x2. Okay, so this scale variable can be pulled out, right? So that is a homogeneous of degree 1 function. Okay, in general, function is homogeneous of degree k if the function satisfies this equation, alpha to the power k. Okay, so degree 1 corresponds to the case k equals 1. All right, so this CS function is homogeneous of degree 1. Okay, because you can easily check by yourself, but yeah, let's do that together to get familiar with this notion. So you have, if you think about alpha x1 and alpha x2, then utility function becomes a alpha x1 to the power alpha to the power r, and b alpha x2 to the power r, and then raise the whole expression to the power 1 over r. Okay, then by the law of exponent, we can distribute this power r to alpha and x1 and alpha and x2. Okay, so we have a common factor alpha to the power r inside the parentheses, ax1 to the power r, bx2 to the power r. Okay, so this r is cancelled by this one, right? So we have alpha ax1 to the power r, bx2 to the power r, and to the power 1 over r. Okay, so that is the original function u. Okay, so after scaling up both variables by alpha, we end up with alpha times the original function, so it is a homogeneous of degree 1. Okay, so CS function is homogeneous of degree 1, and CS utility incorporates the previous utility functions. So these are linear utility and Leontief utility, and even Cobb-Douglas utility function are homogeneous of degree 1. Okay, so this is a so they describe homothetic preferences. So if we know MRS information about one single indifference curve, then we can find out marginal rate of substitutions about every bundle. Okay, cool. And then the last example is a quasi-linear preference. Okay, so it takes this shape. So it has one common example is x1 plus square root of x2. Okay, So it is a linear with respect to one good, but non-linear with respect to the other good. Okay, so it is a quasi-linear preference. Yeah, one property of this quasi-linear. So we call the first good. So utility function is a linear with respect to the variable numerator. Okay. Yeah. So one major property of this quasi-linear preference is marginal rate of substitution is independent of x1. Okay. So if we draw a horizontal line, and if we think about the marginal rate of substitution at these bundles, they are the same. Okay, that is immediate from this the form of the utility function, because mu1 is a constant and mu2, because utility is additively separable. Okay, we have x1 here, and this function phi is a independent of x1. So in case of this, mu2 is 1/2 square root of x2. So MRS is going to be 2 square root of x2. So it's independent of x1. Okay? So this quasi-linear preference is commonly used when we talk about, so when we study auctions or mechanism designs in the future. Okay, so it has a nice property. So one more interpretation is, we usually take this numerator as a money. Okay, so it stands for a transferable utility. So if we have a one individual here and second individual here, okay, so one individual having utility function u1 and another individual having this utility function u2. And suppose that both individuals have a quasi-linear preferences, okay? Then, some amount of utility, okay, that is some amount of money, can be transferred to the other individual, right? So, some amount of money can be transferred to individual one, okay? Then, during this transmission, there is no loss in the utility, so it exists. So it describes transferable utility. Yeah. All right. So in this video, I talked about convex assumption and 5 standard examples, so 5 standard forms of utility functions. So I think this is the end of the first week. I was planning to talk about utility maximization problem, but let me postpone that. So let me postpone that to the second week. So hope you guys enjoyed the video so far, and then hope you guys have a great weekend. I'll see you next week.